Welcome everybody to this special event organized by the Department of Earth, Atmospheric and Planetary Sciences. I thank you all for coming through the winter. Last year we also had very bad weather and we almost had to cancel. And this year, fortunately, there was not a big snowstorm. We had many cancellations already in the last couple of weeks, but not this time, fortunately. And certainly not for a speaker from California. The Brace Lecture, as you may know, honors the legacy of former department head William F. Brace. He passed away just over 3 years ago, but he left a very rich and vibrant legacy for our department and for MIT as a whole. Bill came to MIT as a student in 1943, got his PhD in 1953 from course 12, and retired in 1988. He was department head from 1981 through 1988. And among many of the accomplishments in his tenure as department head was actually the merger of two departments. And some of you may remember that. I certainly don't. I was still in high school at the time. But he merged the two departments, course 12, Earth and Planetary Sciences, and course 19, which was Meteorology and Physical Oceanography. Also what he did in his tenure is to hire many of the faculty that are still around today and made it all, on their own way to leadership in academia. And a fact that is maybe not known by many, but certainly known very well by all the faculty, is that he also initiated the Thursday afternoon lunches with free food for all the faculty. And that still is, to this day, one of the beautiful venues that we have to get together in friendship and collegiality to talk about research and sometimes even do some business. It's an annual event. This is the second time we do it. Last year we had John Grotzinger, and the speaker will be introduced shortly. But I would be very remiss if I don't introduce Peggy Brace. Thanks for coming. Peggy and Bill have been together for most of Bill's life, and he's still sorely missed by everybody, but I know that the person who, of course, misses him most is Peggy, and I'm very, very pleased that you're here again today. Without further ado, I will then pass the microphone on to Bradford Hager. Professor Brad Hager is the Cecil and Ida Green Professor of Geophysics and also the Director of the Earth Resources Lab of MIT, and he will introduce the speaker.
Okay, it's a great pleasure and honor to introduce today's speaker. Tom Jordan is a larger-than-life persona, a man who's cut a wide swath through international earth science, and as I'll describe in a minute. But first, a short digression. One reason that I'm so excited to introduce Tom is that he has had a really huge impact on my career. I remember hearing a talk by Tom at the first AGU that I attended as a graduate student. Okay? And it was a model of clarity, precision, and passion. It inspired me and confirmed, at least to me, that I had made the right choice by entering geophysics. Tom also hired me at MIT, where he and Bill Brace, before him, had assembled a fantastic group of colleagues, including Rob. And as you'll see when he gives his talk, Tom is a master of persuasion. He knew just what arguments would seduce me away from a small technical institute in Pasadena, where I worked then. But it turns out that Bill Brace actually made the argument that clinched the deal. He told me I could ski out my back door in March. Tom's a mover and a shaker, a man famous for his tremendous energy, accomplishment, and little need for sleep. He entered Caltech as an undergraduate at age 16, and only 3 years after getting his bachelor's degree, he got a PhD from Caltech's Seismolab. He immediately joined the faculty at Princeton, stayed there a few years, and then moved on to Scripps. In 1988, Bill Brace hired Tom as the Schrock Professor of Earth and Planetary Sciences, and a year later, Bill passed the baton to Tom, who served as each department head for 10 years, and it was a very exciting decade. Then, having put his stamp on our department, Tom next moved to USC, where he took over the reins of the Southern California Earthquake Center, also known as SCEC. Tom built the SCEC consortium to include researchers from more than 60 institutions, all working together in a big collaboratory. You'll hear Tom's perspectives on earthquakes and their impact on society shortly. Tom's also made seminal contributions in a wide range of earth science. In addition to his work on earthquake physics and seismic hazard, Tom's made major contributions in plate tectonics, structural seismology, and mantle dynamics. Doing justice to the awards and honors that Tom has earned would take the rest of the hour, so I'll just mention only a few. He got an AGU McElwain Award as a hot young Turk in geophysics, and then later on got a Lehman Award for his contributions to earth structure. In 1988, the National Academy of Science elected him to membership, and since then, Tom's played a leadership role in the Academy, including guiding the writing of two important studies, one a perspective on earthquake science. I'll end with Tom's contributions as an educator. Many of his former grad students are themselves leaders in their fields, and Tom's co-authored two textbooks that have wide appeal to undergraduates. I use one of them myself in my undergraduate course. Beyond academia, Tom has played a major role in promoting public awareness of earthquakes, and he's now playing a prominent role, I learned last night, in a National Academy effort to provide better scientific input for various things, including Hollywood productions. So perhaps a different kind of Academy Award is in Tom's future, and Margaret is already shopping for her dress, as I understand it. Okay, so Tom, it's great to have you back here at MIT, and please tell us now about the inference spiral of earthquake system science.
Well, it's a great honor to be invited to give this lecture, and Peggy, a great honor to be able to honor Bill Brace, who was just a remarkable person. He was talented in so many things. His work in rock physics drove forward the science of earthquakes, what I'll be talking about today. But he, of course, had many other talents. He was an exceptional athlete. And I remember, I think it was in the mid-1970s, and Peggy, you can correct me, when he won at least once in his age class the very grueling Pikes Peak ascent. 13 miles, almost 8,000 feet of vertical. And at that time, you could nominate and elect a sports star to be on the front of a Wheaties box. And so, I don't know exactly who it was, organized a campaign, and we all went out and bought Wheaties, and we cut off the box tops, and we nominated Bill Brace for the front of the Wheaties. I don't think that ever happened, but I remember eating a lot of Wheaties. Bill recruited me to MIT in 1984, actually, not in 1988, right after, the year after the merger between Course 19 and Course 12. And so I arrived at a department that was really loaded for bear in terms of doing system science and earth system science. And what I'd like to do today is talk, I wanted to have this picture of Bill up while I was saying this, talk about this legacy and talk a little bit about the field of system science, illustrate for you that science using earthquakes as an example. So the study of complex natural systems, you can order these things by proximity and scale. We can talk about biosystems, ecosystems, geosystems at a terrestrial scale, and of course, out and beyond, the stars and planets form very interesting systems. And I think we recognize, especially in the EAPS department, that this sort of science, this system science, is really extending the typical programs of physics, chemistry, and biology in new directions. And in particular, it provides us with new ways to investigate how we as humans are interacting with our environment. Now, how we do system science I try to summarize that on this slide. We seek to explain phenomena that emerge from nature at the system scale. This can be at a global scale, like the climate system or plate tectonics, or it can be at smaller scales, such as the earthquake systems that I'll talk to you about today. Now, the system is not a physical reality. It's really a representation of nature that we use to try to understand some behavior and predict its future course. So the choice of the target behavior, in the case I'll be talking about earthquakes, really determines what we mean by the system, and in particular allows us to set up numerical models of that system behavior. And of course, those models have to include interactions with the environment in which the system lives. Essentially, all interesting systems and geosystems are open systems. And I would argue that it's this science that provides the framework for most of the basic research in geoscience. And I certainly found as department head here at MIT that this paradigm was important in terms of thinking about how our department was constructed and should move forward. But of course, the predictive understanding of geosystems is so really important for human society, because very often these systems well, this is essentially the world we live in, and many aspects of the systems affect our well-being. Of course, predicting how natural systems might evolve in the future is a very difficult problem. If you look at the scale and the complexity of these systems, their openness to influence in the environment, we can't replicate them in the laboratory, and we have a hard time modeling them numerically. And that's led some people to argue that really one can't predict the future course of these systems using mathematical models. That's actually a quote from a book called Useless Arithmetic, Why Environmental Sciences Can't Predict the Future by Orrin Pilkey and Linda Pilkey Jarvis. I think that is a pessimistic view, and I'd like to argue that if we organize our inference properly, we can make progress in understanding and forecasting how these systems work. And so what I'm going to use as sort of the icon for this talk is this diagram, somewhat complex, that I call the inference spiral of system science. And what we do is we begin by observing nature, and we formulate some sort of a model to describe a target behavior we are interested in explaining. We have to make sure that our model is correct in some mathematical sense or some physical sense, that we're actually, if we're, say, doing a large calculation, we're doing that calculation correctly, and we often call that verification. We then use the model to forward predict some behavior, typically through some numerical simulation, and we try to make those simulations, to draw from those simulations observables that we can compare with data. We then compare with data that we have, often very limited, and if the model can explain those data adequately and is adequate for some particular purpose, we say the model has been validated. Almost never are our models adequate in terms of explaining data, so we have to go back to the model and we have to somehow change the model to better describe what is going on in the real world. And we do that by trying to assimilate data into the model. And then, of course, we go through that process again. We have to verify, we have to simulate, we have to validate, and so forth around the spiral. And as we move outward on this spiral, we typically incorporate better physics, we include more data, and as we'll see, it requires more computation. Now, earthquake systems are particularly interesting, in part because they are so unpredictable. We cannot do earthquake prediction in the sense that the public would like us to be able to do, which is, get out of town next week because there's going to be a big earthquake in Los Angeles. But we know that earthquakes are important phenomena from the point of view of the natural description of plate tectonics and other important aspects of near-surface geophysics, and they're also very dangerous. For many cities in seismically active environments, earthquakes are the largest natural threat. And in fact, since I left MIT and went to the Southern California Earthquake Center in 2000, 800,000 people around the world have been killed in major earthquakes. So it's a very destructive phenomenon. So earthquakes are an emergent behavior of a complex system that we would like to be able to describe. Now, in the case of earthquakes, it's more natural to do this in terms of regionalized systems, such as the San Andreas fault system shown here in this diagram. The ribbons that you see there, there's sort of a three-dimensional projection of the faults in California, and you can see the complexity of this very active fault system. It is, of course, part of the North American Pacific Plate boundary, deformation zone, and it gives rise to very frequent large earthquakes. It's also exceptionally well instrumented. So I and my colleagues at the Southern California Earthquake Center, which include a number of you in the room, including Brad Hager, have worked pretty hard to try to develop earthquake system science, that is, develop representations of active fault systems that can predict earthquake behaviors. Now, there are many types of behaviors that we would like to be able to describe. Fault ruptures, which is a basic process that generates the earthquake, the fault slipping because it's been overstressed. That, of course, causes ground shaking as the seismic waves propagate away from the fault. It can, if the fault is in an oceanic region and uplifts the seafloor or depresses the seafloor, cause tsunamis, which are very destructive, and other secondary effects such as liquefaction, landsliding, and so forth. Now, I would say the fundamental prediction problem of earthquake science is to provide prospective information, that is, information in advance, about these behaviors that are useful for society in terms of preparing for earthquakes and lowering the risks of earthquake disasters. I'm going to focus in this talk on a particular behavior, that is the ground shaking caused by large earthquakes, using California as a natural laboratory. I'm going to begin by introducing you to what we call probabilistic seismic hazard analysis. And there are two concepts I'd like to try and get across. One is aleatory variability, sort of randomness in the system, and the other is epistemic uncertainty, what we don't know about the system that prevents us from making more accurate predictions. I'm going to describe some techniques for ground motion prediction and for rupture forecasting that are based upon new types of models that we've been developing for the earthquake problem, and then speculate a little bit on the future of earthquake forecasting and where it might go in the next 5 or 10 years. So to begin, we need to have some type of forecast of what faults are going to rupture. And we do this by, we of course would like to know exactly when, how big, where the earthquakes will occur. We typically do know where earthquakes will occur. They occur on the, especially large earthquakes, on active faults. We can begin to map those faults. We can observe the deformation that's occurring that stresses those faults using geodetic means. We have information about past earthquakes we can incorporate into our models. And out of that, we typically come up with some statement of how frequent large earthquakes on particular faults might occur. Not exactly when, but how frequent. This is a model that will be released in about 10 days, I guess, on March 10th. It is the latest version of the Uniform California Earthquake Rupture Forecast developed by the Working Group on California Earthquake Probabilities, which is sort of a joint venture between SCEC, the U.S. Geological Survey, and the California Geological Survey. And that gives us very important information over the long term of what types of seismic activity we might expect on various parts of the San Andreas fault system. But of course, knowing about the fault rupture is not enough. We actually know what effect it's going to have on, let's say, our built infrastructure. So we have to be able to forecast how the ground motions generated by that earthquake will decay as we move away from the event. We know that we're very far away, the ground shaking will be low. If we're very close to the event, the ground shaking will be high. But exactly how that dependence on distance, dependence on magnitude, dependence on other aspects of the faulting, what that relationship is typically described by a set of empirical equations which are known as ground motion prediction equations, or GMPEs. And from those GMPEs, we can obtain measures of the intensity of shaking in terms of a probabilistic description of that intensity. So this is something called a seismic hazard curve. What's being plotted here is the peak ground acceleration. This is on a logarithmic scale. And on the vertical axis, it's the probability of exceeding that ground motion in a particular period of time, in this case 50 years. So this happens to be for downtown Los Angeles. And this locus, this red line, is what's called the hazard curve. So for example, if we look at the probability of, let's say, 10% in 50 years, we move over to this diagram, we can see that there is a 10% chance of exceeding the ground motion of about 0.6 g at this particular site in that 50-year period. If we lower that probability, we can see that we get a larger ground motion that might be exceeded in that period of time. So this is the type of diagram that's extremely useful to earthquake engineers and others that are trying to prepare for seismic disasters. We can take, so this is calculated at a particular site, in this case downtown Los Angeles. We can fix a value of probability, let's say this 2% in 50 years, that would be a value of about 1 g, that is the ground accelerations would be equal to that of gravity. Can actually throw things up into the air. I remember a story after the Loma Prieta earthquake. I went to visit the area where the faulting had occurred in Northern California, and they took me to a cabin. There was a big picture window, and they said a guy was sitting there washing dishes. When the earthquake happened, it threw him through the window out onto the ground. So that tells you there are accelerations that can be as high as the acceleration of gravity or higher. And if we were to now map that peak acceleration as a function of position, we get something called a seismic hazard map. So here is a seismic hazard map for Southern California, which I'm going to use to focus on. And this happens to be for, well, there's no scale on here, but this is actually a map of 2% probability of ground exceedance, of peak ground acceleration in 50 years. So we go from the earthquake rupture forecast using the ground motion prediction equations to various types of intensity measures. Now, this probabilistic seismic hazard analysis, as it is currently practiced, is based almost entirely on empirical statistical models. And one of the things that we seek to do is to improve these models by adding some more physics, more understanding of, for example, the way waves propagate from the source outward to some place of interest. So we can build a different type of model, one that instead of using ground motion prediction equations, empirical ground motion prediction equations, actually uses the wave equation to calculate how the waves will propagate through the complex geologic structures in the region and generate ground motions, that is seismograms, and from those seismograms we can calculate various intensity measures. Now to do this, we actually have to extend the earthquake rupture forecast. These empirical earthquake rupture forecasts don't have enough information for us to do this simulation, so we actually have to add more information. I won't go through the details of that. We have that's possible to do, but it brings in other physical assumptions. Ideally, we'd like to get rid of the empirical earthquake rupture forecast and be able to simulate the fault ruptures, or the, at least in a statistical sense, the fault ruptures, using some model that accounts for how the stresses accumulate and are released and are transferred from fault to fault during the seismic, during some seismic sequence. And for that, we can use earthquake rupture simulators. I'll speak briefly about those. Now, let's go back to these ground motion prediction equations and ask, why not just do business that way? Well, here's an example of some plots that show empirical data in red dots as a function of distance on a logarithmic scale. Again, you're looking at peak ground acceleration. And what the ground motion prediction equations are, basically a description of how these data fall off with distance and perhaps other parameters such as magnitude. So here's for magnitude 6.0 events, here's for magnitude 7.5 events, and the red lines would represent the estimated values. And what you notice about these, this diagram is that, first of all, in close to the faults, there's very little data. So we actually don't know what the shaking might be from empirical observations, because we don't have many empirical observations. So we have an uncertainty. That uncertainty we call epistemic uncertainty. It's uncertainty in our knowledge. If we had more data, we could reduce that uncertainty. There's also just a large scatter in these plots. And this is a variability that's just not captured by the explanatory variable, in this case distance or magnitude. The data show variations that are not accounted for by the model. We call this aleatory variability from the Greek word for dice. So we'd like to reduce the aleatory variability. We'd like to reduce the epistemic uncertainty. Let's see what that looks like in current ground motion prediction equations. So these are maps of the Los Angeles region. Downtown LA is about here. USC is about, oh gosh, I guess where the O is in Los Angeles. And what you're looking at here are some colors. These colors represent the ground motions at some probability of exceedance. This is 2% in 50 years, the example we used before. And what is contoured here is the peak, is not the peak ground acceleration, but an acceleration at a period of about 3 seconds measured in units of Earth's gravity. So places that are warm colors like red are high values, blues represent low values. Now these 4 models, there's 4 different GMPEs shown here. Each of them is a model that's been published and validated in the sense that it fits the available data, but you'll notice that they're quite different. For example, if you look at the near fault amplitudes, you see some red in some models, such as the one in the lower left and the upper right, whereas the other models, like in the lower right, show much cooler colors. Also look, there are certain places, hotspots, that correspond to sedimentary basins. This one here, for example, is the Santa Clara River going down to Ventura, and it's a region of soft sediment, so expected that there is going to be high ground motions here, but notice the variations from model to model in those predicted ground motions. So this is an example of epistemic uncertainty. Different modelers get different answers because we just don't know which model is right. Now, the National Seismic Hazard Maps, which are used for the in building codes and to guide engineers on how to build appropriate structures, are based upon an average of these 4 models. Just, well, we don't know which one's right, we'll just average them up. So that's an example of epistemic uncertainty. But remember, there's also the aleatory variability. Now, the aleatory variability, so let's suppose we're trying to predict some ground motion parameter y. We do this in terms of logarithms. We have some mean value or some expected value given some explanatory variable, such as distance or magnitude. We have something left over. And this, what is left over is the aleatory variability. It's typically described, we have explanatory variables and we have the aleatory variability. Epsilon here is just a normal variant with a unit variance, and sigma t represents a scale that when it's small represents small aleatory variability, when it's large, large aleatory variability. Now, the ground motion prediction equations give us hazard curves. This looks different than the hazard curves I showed you before, concave downward. That's because this is plotted on a linear scale. But the current GMPs give a value shown here in red. And you can see if we had, and that's because we have a typical aleatory variability of about 0.6 in these units. Notice how as we go down in aleatory variability, the hazard goes, the probability at a given hazard level, let's say 1g, goes down. So turning that around, at constant value of, let's say, distance and magnitude, increasing the aleatory variability increases the exceedance probabilities, and you can see by quite a bit. Now, this is pretty important from the point of view of engineering, and engineers try extremely hard to reduce this aleatory variability, but they haven't been very successful. So this shows you a plot of the sigma sub t, the measure of aleatory variability, as a function of time. The first early seismic hazard studies were done back in the 1960s and 70s. Things really got off the ground in the 1980s. Been lots of studies, but notice how the value of this sigma sub t has been persistently more or less a constant, plus a lot of scatter, at a value of about 0.62. Some people call this type of aleatory variability irreducible. It's an intrinsic property of the system that you just can't get rid of. But of course, that's incorrect. It depends on the model of the system. So for example, if we have a model, let's say a GMPE, a statistical model, it'll have some aleatory variability, some epistemic uncertainty. We'll just stack those on top of each other as variances that might add if they're independent. What we can do is change the explanatory variables. For example, introduce a physical model or a physics-based model where we have more explanatory power. That will reduce the aleatory variability. Now, because we might have a lot more model parameters, it might actually increase the epistemic uncertainty. So we might actually have a larger total uncertainty. But that epistemic uncertainty, by better observations, better physics, better calculations, can be reduced. And so we can eventually start to nail down these things. Now, how are we going to do this in terms of ground motions? We're going to do it with simulations. Here's an example of a simulation for a large earthquake on the San Andreas Fault. And I'm going to just show this as a series of snapshots through an animation because I don't ever trust projectors to animate things properly, but it's a nice movie if you want to see it. This is 10 seconds after a rupture initiates at the very southeastern end of the San Andreas Fault. This dashed line shows the San Andreas Fault, actually shows the rupture that we're going to see rupturing up the San Andreas Fault to about the central part of the Mojave. San Andreas, of course, continues into Northern California. And what I want you to look at is the amplitude of the seismic waves, which are indicated by the colors. So the yellow is very high amplitude, the red's lower amplitude, as the wave propagates, or as the fault propagates to the northwest. So this is now, after about 28 seconds, the fault has propagated at a rate of about 3 kilometers per second up through the Coachella Valley. And you can see very high amplitudes out in front of the propagating rupture. This is an interference effect that we call the directivity effect that is associated with a propagating rupture of this sort. And as it moves up the fault, you can see that big directivity pulse, but then something happens. The waves sort of take a left turn. Well, you can still see the directivity pulse, but you'll see all this energy that gets funneled in, essentially coming in through the sedimentary valleys that act as big waveguides that sort of funnel this energy into the Los Angeles region. And this causes shaking much higher than would be anticipated in, let's say, another geometry. And these motions can go on for a very long period of time. You can see this is after 2 minutes. We still have fairly high shaking in the Los Angeles basin. Now, my wife, Margaret, sitting up there, is muttering to herself, why did we move to LA? All right? And I always tell her, I said, well, you know, if you want to hunt elephants, you got to go to elephant country. So that's why we live in Los Angeles. Okay, so we can actually do this not only as an individual simulation, because of the power of modern computing, we can do this on a very large scale. In fact, we can start to sample the earthquake ruptures in essentially a Monte Carlo way. We can model many different types of ruptures. For example, a given patch of fault, if it ruptures, it might rupture this way or it might rupture that way. There might be a strong displacement on the fault here and a weaker displacement here, or some very patchy displacement. Lots of variability. We study this variability. We can quantify that statistically. And we have a platform that allows us to do these probabilistic calculations called CyberShake that I'd like to describe. It essentially follows that blue pathway through ground motion simulation. And what comes out are seismograms. And from those seismograms, we can calculate hazard curves and we can calculate hazard maps. So here's an example of a calculation done for the Los Angeles region. We can actually do this calculation fairly efficiently. And this shows you the results for a set of sites around the Los Angeles region, adequate enough to be able to interpolate a seismic hazard map. It includes all of the ruptures in the Uniform California Earthquake Rupture Forecast version 2 that are within 200 kilometers of the site. That's about 15,000 ruptures. And then we allow each of those ruptures to have variations, propagating this way, propagating that way, different patchiness in terms of the type of slip on the fault. We end up calculating a total of about 400,000 different ruptures for each site. And we calculate that for different components of motion. So when all is said and done, we end up with about 240 million seismograms that represent the probabilistic sampling of this seismic hazard model. And from that, we can construct probabilistic seismic hazard maps, just like the ones you saw constructed from the purely statistical GMPEs, only now we're using deterministic simulations rather than probabilistic descriptions of actual data. Well, this shows you, of course, to do this, you have to be able to know the three-dimensional structure of the Earth. And we don't know that structure exactly, but in the case of Los Angeles, the structure is extremely complicated. There are sedimentary basins, there are mountains, faults that divide one region from another. This shows you the difference in the seismic hazard map that you would get if the Earth were one-dimensional, that is, there was only a depth variation in the seismic velocities, versus, on the right-hand side, a fully three-dimensional model. Now notice that along the San Andreas Fault, the San Jacinto Fault, there are lots of faults in here that are represented, but these are the big players. You can see this big red track. This is because in one dimension, those big directivity waves just propagate along the fault unimpeded by lateral variations in Earth structure. Whereas in three dimensions, when we put in the full three-dimensional variability, you can see that the amplitudes along the fault on average are lower. That energy gets scattered out, and it gets scattered out into, for example, the sedimentary basins. Remember I said the sedimentary basins can act as waveguides. They can trap energy. You can get resonances within those waveguides that increase the ground motions. And that's exactly what we see in the three-dimensional model. Certain basins with deep sediments, such as here in the Ventura area or out here in San Bernardino. By the way, I've learned one thing. Don't live in San Bernardino, okay? It's a big sedimentary basin right on the San Andreas Fault. And what happens is those big directivity waves couple into the basins. We get what we call directivity basin coupling that really amplify the motions. And in fact, because of that energy I showed you in the simulation that comes into the Los Angeles region, you can see much higher amplitudes here than would be expected from the one-dimensional model. Now, this is a little bit of a complicated figure, but I want to explain it. What we're looking at here is there's 4 stacks of colors here at different periods of seismic motion. This is 2 seconds, 3 seconds, 5 seconds, and 10 seconds. So these are at what we would call long seismic periods. We'd like to be able to do these calculations at 1 second, a tenth of a second, and so forth. But right now we can do them at longer periods. And what we're looking at here is the total residual variance. So I'll explain what that means. This dashed line is the aleatory variability. That's just the sigma sub t in those ground motion prediction equations. And these are the ones that are actually used in the National Seismic Hazard Maps. So I said that sigma sub t was about 0.62. The square of that is about 0.4 something. That's this point here. Now what this stack of colors represents is the total variability that you get if you use the CyberShake simulations as data and try to predict those data using the GMPEs and look at what's left over that you don't predict very well. And you'll notice that that column is the same height as the actual sigma sub t in the ground motion model. So what that's telling you is that the variability of the ground motions that we see in the Los Angeles region are comparable to the variability of the data we see worldwide that were used to develop the ground motion prediction equations. But what's interesting about this is because we have, this 240 million seismograms, we can actually take apart this variance into component terms. And I won't go through technically how that's done, but it's essentially done by a type of averaging that gives us statistically independent measures that correspond pretty much to what are in the GMPs, that namely site effects, path effects, directivity effects, variations in magnitude associated with stress drop, and of course the source complexity effects because the motion is so irregular. Now, there are certain parts of that, this, for example, the directivity effect and the magnitude variation, the slip complexity, that are effectively, we don't know how to explain them other than statistically. We can't predict them. We can't predict which way a fault is going to rupture as yet. That's a big research problem. But We just have to assume that sometimes it'll rupture this way and sometimes it'll rupture that way. That's a form of aleatory variability that we can't reduce within this particular model. However, the site and path effects are described by the three-dimensional structure, and if that three-dimensional structure is good, then the model will explain that variability. So that is an epistemic variance that in principle we can reduce down. In fact, we think the epistemic variance in these models is actually much lower than the size of those error bars. So I guess the conclusion here is that we can, by using earthquake simulation, physics-based simulation, reduce epistemic or reduce the variability that we see in the current ground motion prediction equations by about a factor of 2 in variance, and that corresponds to going from a sigma t of about 0.62 to 0.43. That's out at large hazards, let's say out here close to 1G, that's a factor, that's almost 2 orders of magnitude reduction in the probability if you fix the X and the Y bar. That is a big deal. I'll give you an example. Pacific Gas and Electric has 60 federally regulated dams plus a nuclear power station in California. Those dams were built in the 1920s. They've got to be seismically retrofit. PG&E estimates it will cost $30 billion for the seismic retrofit. Therefore, they very much want to be able to do that appropriately, and that means to know which dams are going to see large ground motions, which ones are going to see small ground motions. Right now, everything's all mixed together. They can't differentiate, so they have to build everything to be very secure. But by reducing these types of variability, they get a more accurate representation. And in fact, when we actually compare the ground motion prediction equations, this is the new 2014 values shown in dashed lines with the cybershake values, you see exactly that kind of reduction in certain sites like Los Angeles. Now, that reduction only occurs if you have the same value of the explanatory variable. But what that means is that someplace you're going to get a reduction and someplace you're going to get an increase, because what you're saying is the model can predict where you'll have high values and low values. And in fact, that's exactly what we see. I'll use again San Bernardino as the case. Don't go to San Bernardino. Here, cybershake shows even higher values than the ground motion prediction equation. Notice how much higher the probabilities are, let's say at 1G in San Bernardino than they are in Los Angeles. And that's because of the strong basin effects and the fact it's close to the San Andreas Fault. Now, of course, to do these calculations, you have to put in a lot of information about the Earth. And the two basic components are the earthquake rupture forecast, where we use the so-called USERF model, and you also have to put in some estimate of the three-dimensional structure of the Earth. Now, how do we get the three-dimensional structure of the Earth? Well, seismologists have techniques called seismic tomography, which allow you to take observed seismograms and invert them to get back at the Earth structure. We have now very powerful tomographic techniques, and we are producing new models. This is a model we just published in JGR a few months ago of Southern California. I don't know if you can see the state shorelines over here. Los Angeles would be right in here. This is the Garlock Fault, the San Andreas Fault. What you're looking at is the Earth structure at 2 kilometers depth, 4 kilometers, 6 kilometers depth, 8, 10, 12, and so on. This particular model was obtained from a three-dimensional model, but iterated using a lot more data. In fact, we're using data sets as large as are being used for global tomography. Just to show you more of the model here is if we go deeper, blue colors are higher velocities, red colors are lower. This is 14 kilometers, 16, 18, and so forth, down to close to the base of the crust at 24 kilometers. There's all kinds of interesting features in this model. For example, the Sierra Nevada at great depths are lower velocity than the Peninsula Range batholiths, even though we think of them as being geologically quite similar. But what I want to emphasize for the purpose of this talk is that in order to derive these models, we use exactly that inference spiral that I mentioned before. We take some model, let's say some model we're given, a starting model, we compute synthetic seismograms, we then compare those with actual data. We see that they don't fit the data that well, so we do some sort of inversion to improve the model to fit the data. We verify the model, and then we recompute all the seismograms through that three-dimensional structure and go through this process again and again. And the model I showed you iterated 26 times. So this is this cycle, or the spiral of inference that I was talking about. And here's some of the results. Here's the model we started with. This was a three-dimensional model developed by the Southern California Earthquake Center over a number of years. And what you're looking at here is essentially the thickness of sedimentary basins. It's a particular measure. It's actually an isovelocity surface for 2.5 kilometer per second shear wave velocity. And what you see here in the starting model is the Imperial Valley and basins in the Los Angeles region, something up along the San Andreas. But you'll notice that most of this map is blank. That's because we didn't really know what the sedimentary basin structure was, or at least it wasn't built into the model. When we do the inversion, we bring in the very deep Great Valley Basin, the San Joaquin Basin. Look at this one in China Lake. See how it wraps around this fault? This is really a pretty accurate representation of the basin. This model doesn't know about faults, so that's a verification step. We get deep sediments in the Antelope Valley, the offshore, and so forth. It's very important to map those sedimentary structures because remember, that's where the energy gets trapped, and that's what causes the really strong ground motion. So we think these models are much better at predicting the ground motions, and we can test that. Here we had an earthquake this last year after this model was completely developed, and so we can take this earthquake, the La Habra earthquake, on March 28th, just about a year ago. It wasn't a big earthquake, magnitude 5.3, and we can calculate synthetic seismograms, compare them with observations at various stations. Here's just a selection of stations around the earthquake. I just want to point out the exceptional quality of the fits to some of these stations. These are fairly low frequency waves, about 0.2 hertz, 5 seconds period. But you'll notice that they're fitting almost wiggle for wiggle over 3 different components and path lengths on the order of 300 kilometers. I never thought in my lifetime that we would see this type of fit to data. Now, there are other places where we don't fit the amplitudes of the phase too well, but we think we are starting to get a real handle on this. And when we look at 300 stations distributed over Southern California and kind of contour how well we fit, here in red colors meaning a very good fit, blue colors meaning a lousy fit, here we're comparing the iterated model with the starting model or with another model that we have. This is one from that university down the road, what's it called, Harvard University, another model for three-dimensional structure. We can see that this iterated model fits much better. And this is a prospective test. These earthquake, this shows you how well the CyberShake model can do. Now, of course, we have a lot further to go. The seismic band is fairly broad, goes from thousands of second oscillations of the whole Earth to very high frequencies. Typically, in seismology, we like to study that whole spectrum, but from an engineering point of view, we are interested primarily in the higher frequencies because tall buildings will resonate on the period, with periods on the order of a few seconds. Houses are sensitive to energy greater than 1 hertz, and very stiff structures like nuclear power plants out here at 10 hertz or higher. So we have to push these calculations out in frequency. Right now, CyberShake goes to about 0.5 hertz. We have a plan to get this up to about 5 hertz within a few years. But that requires that we solve a number of physics problems and improve our physics in terms of introducing realistic fault structures, including fault roughness, near-fault plasticity. We have to deal with the frequency dependence of attenuation. We have to deal with topography, small-scale, near-surface heterogeneities, things in those sedimentary basins we can't resolve with tomography, and so forth. And that's a big job. We're working hard at that, and it takes a lot of computer resources. This shows you the resources we have on national supercomputers for this next year, or as a function of time, actually. For this next year, we have about 362 million computational units or service units, essentially computer hours, that we have on these large computers. That's 1 million hours a day that we are burning on large supercomputers doing these calculations. Of course, computers are getting faster. If we look at the speed of computers, as measured here in teraflops per second, of course, computers increase their performance with time. This is something we call Moore's Law. But you'll notice that the SCEC simulations are actually catching up and becoming more efficient relative to current computational capability As we add more physics, we're going to be needing more computing. And frankly, we're anxious to get up to extreme scales, including exascale. Now, I want to come back to the problem. We've been talking about seismic hazard analysis using long-term forecasting. I want to come back to the problem of how we do that forecasting. You know, we've all would like to have what we call deterministic earthquake prediction. I call it the silver bullet approach, where we have some sort of diagnostic signal that we can see in the data, and we say, oh, wow, look at that. There's a movie coming out called San Andreas. There's a Caltech scientist, turns to another Caltech scientist, and goes, oh my God, the radon reading is up to 80. We better get out there. Of course, the other scientist goes out there and immediately gets killed by the big earthquake. We can't do that kind of deterministic prediction. It hasn't, 100 years people have been trying to do this. It hasn't turned out to be successful. So we've turned to this system science approach. You might call it a brick by brick approach. And that has produced viable methods, both in terms of long term, which I've shown you, but also in terms of short term. And I want to talk just a little bit about that short term, don't have too much time. But if we think of this fundamental prediction problem as providing prospective information, a long-term forecast would read like this. Earthquake shaking having a peak ground acceleration of 1G or greater will occur in downtown Los Angeles with a 2% probability in the next 50 years. That's what I showed. That was an example I showed earlier. Deterministic earthquake prediction would say earthquake shaking having a peak ground acceleration of 1G or greater will occur in downtown LA during the next month. Notice no probability, just a statement it's going to happen. We replace that statement with something different. It's again probabilistic. Earthquake shaking having a peak ground acceleration of 1G or greater will occur in downtown Los Angeles with a 2% probability in the next month. 2% probability in the next month. Is that good? Well, that's a probability gain of 600 relative to the long-term forecast, right? We've increased the probability by a factor of 600, but it's still a pretty low probability. And so the question is, what do we do with that type of probability? Well, we know that's important because we have seen sequences around the world. This is showing the Canterbury earthquake sequence in New Zealand, which was very destructive. It started off with a magnitude 7.1 earthquake, the Darfield earthquake, on September 4th, 2010. But it was actually an aftershock on February 22nd, only magnitude 6.3, occurred right beneath the city of Christchurch that really destroyed the city center, killed 180 some odd people, and there were further aftershocks that compounded that damage. Well, we know the seismic hazard in Christchurch is no longer what we thought it was before, when there was very little earthquake activity. We're now seeing a lot of earthquake activity. We have to somehow factor that in. And the way we do that can be illustrated here using the Canterbury seismic sequence. This is the date as a function of time, starting with the Darfield earthquake, and this is the number of earthquakes that were observed. And what you see is you get the big earthquake, and then you see all kinds of earthquakes, a very sharp rise in the number. This is the aftershock sequence, and you'll notice how that curves. Well, if you look at the distribution of magnitudes in this sequence, it obeys a very simple scaling relation. There's an increase by a factor of 10 every time you reduce the magnitude by 1 unit. That's a very nice scaling relation called Gutenberg-Richter scaling relation. But you'll also notice that this number of aftershocks, this sort of logarithmic character, corresponds to a probability in time of 1 over time. So the number of aftershocks decrease like inverse time. The other thing you'll notice is that this big earthquake had a lot of aftershocks. The ones that followed the smaller aftershocks themselves had aftershocks, but a smaller number of aftershocks. And so we can say that, another scaling relation, that the number of aftershocks scales with the magnitude of the main shock. We can put all that together and we come up with a statistical model that allows us to forecast earthquakes in the short term. And these models have been deployed in New Zealand, being in process of being deployed in Italy, they're being developed in California. And the question is, should these short-term forecasts that have high probability gain but low absolute probability, be used publicly? Is it useful information? And there's a big debate going on within seismology and earthquake science as to whether this type of operational earthquake forecasting should be deployed. And of course, one of the problems is that it's the small probability. I mean, you can't, if you have a probability gain of a factor of 1,000, but the probability is only 1%, you can't tell people to evacuate their homes. You would have to take much lower cost measures. And the utility of this actually hasn't been rigorously demonstrated. There's also a standardization of protocols that has to happen. And what's probably most important is that we have to make sure that this type of forecasting is itself accurate. So we have developed a international collaboration called the Collaboratory for the Study of Earthquake Predictability, or CSEP, which actually tests these short-term earthquake forecasts using data that are being recorded in various regions, such as in California, in Italy, and importantly in places like New Zealand and Japan, where there's a lot of earthquake activity. And you can see that in Japan, there are 203 models being tested. In New Zealand, 60 models being tested. And so these earthquake sequences that are occurring in these countries are giving us the ability to verify and to validate these models. And this shows you an example of what's coming out. I don't want to go through the technical details of this diagram, but suffice it to say that what it shows is that the short-term models typically provide probability gains as advertised of about a factor of 1,000 relative to the long-term forecasts. So they are, in fact, accurate representations at low probability. Well, I'm sorry, the short-term probabilities, I should have mentioned that. Typically, the probability decays like 1 over time after each event and increases with every other event. So the time scales are typically good for days to weeks, I would say, are most useful. But these things actually have utility out for years, and we can extend them. One of the issues, and this sort of shows it here, is we have long-term models that are represent the hazard over, let's say, timescales of 50 years. And those represent a type of model where we say, okay, the fault is being stressed by plate tectonics. It ruptures. That reduces the stress. The stress has to build up again, ruptures again. So you get a cycle of earthquake activity, very aperiodic, that corresponds to this sort of renewal process. The short-term models are very different. They correspond to seismic clustering. You say one earthquake happens, it's more likely for another earthquake to happen. So you can see these types of models are diametrically opposed. One is less clustered than Poisson, the long-term model, whereas the short-term models are more clustered than Poisson, or than random. And so there's a gap between these models. Now, we have models like the USERV 3 forecast that will be released in 10 days that are beginning to incorporate both the short-term statistics and the long-term statistics. But we're patching across this medium-term gap. By using other types of models, and in particular earthquake simulators that account for the buildup and release of stress and also account for the nucleation associated with triggering and clustering, we think we can span that gap. And this shows you the first results from CSEP testing, where we test the physics-based models against the statistical models. And what we're seeing with for the first time, we're seeing that the physics-based models, in fact, provide larger probability gains than the statistical models. And so we think that is going to be the way that these forecasts develop. Now, I don't think I'm going to go through the details of this, but there are physics-based models that now can actually represent the full complexity of fault systems such as the ones we have in California. And when we apply those models, we can span that gap from the short term to the long term. There's a lot of work left to be done. I think I'm going to skip this slide just from the point of time. But I think we sense some urgency in trying to get this done. And let me explain why. This shows you a map of California. This is the San Andreas Fault. There's a creeping section where there's typically not very large earthquakes. And we know that the Pacific Plate is moving to the northwest relative to North America at about 5 meters per 100 years, 50 centimeters per year. We have earthquakes on the San Andreas Fault that are taking up in part that displacement. In 1906, there was an earthquake that ruptured the northern San Andreas Fault, magnitude 7.8. In 1857, there was an earthquake along the southern San Andreas, again magnitude 7.8. There was one in 1812, a little bit smaller, and one at the very southernmost end that occurred in around 1720, actually 1690 to 1720, a little bit uncertain. Now, if we calculate the time since that last earthquake, it's something we call the open interval. And this shows you the numbers. It's on the order of 100 years in Northern California. It increases down into Southern California, as in fact on the order of 300 years for the southeasternmost section of the San Andreas. So this comes back to you might say the southern San Andreas Fault is locked and loaded. It's actually accumulated enough strain within that system to produce some very large earthquakes. And when we look at the seismic data, we see that in fact the interval since the last earthquake is greater than typical intervals that we see in the paleoseismic record, that is the geologic record of earthquakes that goes back into the past. And the question is, what is going on? The simulators provide us with some idea. This shows you a catalog from 2 simulators for thousands of years. This is, of course, we can do this on computers. This is simulated by Jim Dietrich, one by Steve Ward. And what you see are, if you look at averages over long periods of time, this is a running mean of about 100 years, you see large variations in seismic moment release on the order of plus or minus 50%. So our long-term models, which are assuming that the seismic release at long-term is smooth, may not be correct. We call these seismic supercycles, and the existence of these supercycles might explain why we have such long open intervals. The distribution of open intervals is actually not consistent with our rupture forecasting models. There's something a little amiss. And one possibility is that we're at the bottom of one of these supercycles, and the question is, how quickly might we emerge into a period of large-scale seismic activity? And the thing that keeps me up at night is a diagram like this. This comes out of one of the simulators showing you how you could, if you're in one of these, if you come into one of these high release periods in the supercycle, that you can get multiple large earthquakes. It's just a simulation, but you can see a magnitude 7.8 earthquake along the Mojave section near Los Angeles. Then 2 days later, a magnitude 7.5 along the San Bernardino section. And then 100 days later, a magnitude 7.6 on the Coachella section. We don't know that this is the type of thing that might happen in California, but it gives us pause and makes us want to understand those long-term variations. So let me just conclude by just putting back up this diagram of how we're trying to replace the empirical models with physics-based models. And I think within a period of 5 to 10 years, we will be in a position to where the physics-based models will be providing us with more reliable forecasts than the purely statistical models. I'll leave my conclusions here. Thank you.
I'm Eric. I noticed your inference spirals outwards. That suggests there's never going to end. Of course. Is it a long-term job prospect?
Absolutely. I mean, the question is, we go through these repeated cycles of model improvement, and this actually happens on many scales. As you saw in the tomographic models, we're iterating these things all the time. Right now, we're doing a big study of Central California where we're doing tomographic iterates once per month, all right? And each month, we're adding new data into the pot. We're getting better and better models as we move forward. While that's being done, we're of course also iterating other aspects of the problem. So for example, the earthquake rupture forecast. So there are many wheels within wheels, and all of these things are going to have to spin for a long time before we gain appropriate confidence in these physics-based models. But I'm pretty sure that over that long time, we will be able to capture whatever predictability there is in the system.
Oh, Rob. Thanks, Tom. That was really great. Two things. Is there any evidence in the paleoseismic record for the sequence of 3 earthquakes that close in time?
You can't tell from the paleoseismic record because you can't date you can see events, but you can't date the events accurately enough to know whether they occurred within the same year or within the same century. I mean, it's sort of a half a century uncertainty if you go back just a few hundred years. So we can't actually directly determine that from the paleoseismic record using existing techniques.
How about a 15-meter offset? Is there any indication that?
In paleoseismology, it is possible by careful work to determine the offset that occurs, not just the fact that an event occurred, but what the offset was. It's difficult, expensive, time-consuming. There is, to my knowledge, not any evidence of a 15-meter event on the San Andreas Fault, but people are starting to get at least rough estimates of some events being larger and some events being smaller.
We know from the work of Ed Lorenz that, say, numerical weather prediction, you can't project out more than an editor, a synoptic timescale. Is there any analogous kind of theoretical work in your field that might say you cannot predict the initiation of earthquakes?
Well, it's a debatable point. The question of whether, these systems are certainly chaotic in some sense. Take, for example, the prediction problem. If I have an earthquake that nucleates, and I say, okay, I know that event has nucleated, what can I say about when that event stops? I mean, we know most of the time the earthquake stops because it's just a small event. Every once in a while, that rupture will continue and propagate and end up as a large event. That process is probably very chaotic, in some sense not easily predictable.
So are your systems looking for precursors to larger events, or are you just looking at the statistics?
We're not looking for precursors in the direct sense of the term. What we are looking for are statistical correlations within the system. I mean, it would be, I suppose, like, what do you guys call it when you get these kind of structures within chaotic systems, large-scale structures. I forget the name, but we're looking for those types of structures.
That was a very practical question. You made comments about San Bernardino, but obviously with the physics-based models, that's now a sort of big center of attention. The risk has gone up hugely. To what degree is this being handled in the codes and in the actions taken to retrofit and mitigate?
Yeah, so in the case of a place like San Bernardino, even with standard GMPs, you would get a high hazard, and we know San Bernardino has a problem. The physics-based models would say it's even larger than you thought. But you look at San Bernardino, unlike Los Angeles in 1988 passed an ordinance that said you have to retrofit unreinforced masonry buildings. Those are the most dangerous buildings. San Bernardino hasn't done that yet. So the implementation of building codes is typically a local decision, and local decision makers have to decide how much they're willing to risk. And I think part of our job is. Pardon?
Taxpayers in the rest of the country are going to pay with their buildings.
Yeah, that's true too. I mean, I think we're making some progress. For example, Mayor Garcetti in Los Angeles just a few weeks ago announced a program where certain types of buildings, for example, the soft first-story apartment houses, will have to be retrofit. So there is more movement towards either mandating retrofits or certainly qualifying buildings, saying which buildings are bad and which buildings are good. But of course, as you can imagine, there's a lot of resistance to this within certain communities. So these become political questions.
Yeah, you mentioned the physics of the fault zone itself, and at least one slide. And is there any likelihood of progress in that direction in terms of getting into the nitty-gritty of what's going on?
I think so. Let me give you an example. I didn't have enough time to work it into the talk, but let's take this problem of directivity. You saw that if a fault ruptures and propagates in a certain direction, you get a lot of energy that's kind of shot out that gun, right? So if we could actually predict directivity, which direction the fault might rupture, it would be a huge boon for seismic hazard analysis, right? If we knew, for example, I could show you the figure, I showed you a simulation of the energy being directed into Los Angeles. If that exact same earthquake were to occur, but started at the other end and propagated towards Mexico, it's Mexicali that gets hammered, not Los Angeles. There is some hope that we'll be able to at least make better probabilistic statements about those types of fault rupture phenomena in the future. And that will help improve our predictability.
Is there any system of measuring that directionality and giving them 1 minute warning time to
Sure. So earthquake early warning is currently being developed in Los Angeles. It's already been deployed in several countries, Japan most notably. And there's been a question of how to fund these systems in these lean budget times, but I'm guessing within the next, there is already a semi-operational system that could provide that 1 minute of warning for the type of earthquake I showed in Los Angeles. And those systems will be fully deployed probably within a few years.
Thanks, Tom. I'm getting a message from the man responsible for the elevators running slowly. And he would like to say something.
Something's never changed.
Thanks very much, Tom. I have two points to make. One is to Margaret. I think, Margaret, it's about time to go to the East Coast to give you probability. You don't need to hunt elephants. You can also simulate them. You can do it from the East Coast. Second comment is going to the elevators. There is a reception right now starting in the green building, so everybody's welcome. So it will take some time to go to the elevators. If you have further questions then from Tom, then of course you can answer them. With that said, Tom, thank you very, very much for the
See you all back in the green building. Thank you.